Hey, what's up everyone? Welcome to the stream. So technically today is episode 100, which is pretty awesome. Now normally I guess people have something special for episode 100. I can't say that I have anything other than the fact that I'm actually going to stream. So, you know, as I said last stream, it has been a while. But last stream I spent the entire stream just talking about what's been going on and sharing the changes I've made to Vectrexy. And this stream, I'm going to just get right into it. So now the plan, as I said last time, was, I guess I'm going to talk a little bit. So let me just open up here my plan. I'm just going to get that open here, just so that you know where I'm going with all this. Okay. Is this it? Okay. Let me bring that here. Zoom in a bit. This is my to-do list. So yeah, a bunch of stuff in here that I have to do. Now, where did I put it? Okay, let's see here. So here's all, okay, so here's all the debugger stuff. And as I said last time, I'm going to be working on ultimately implementing the debug adapter protocol so that we could do source level debugging of a C++ or C program compiled for the Vectrex. So along those lines, I put down a bunch of stuff that I need to do. Now, some of these are not related, but one thing I know for sure that I need is this call stack tracking. The debug adapter protocol has some of the queries that it makes are for the call stack frames. It uses this so that it can actually show you the call stack when you're debugging, as you would expect in a source level debugger. And the thing is that there is no such thing as call stack frames on the Vectrex, or at least on the 6809. Unlike modern architectures where you typically have like a register for like the base pointer of your stack frame, and every time you call a function, a new stack frame is created and the base pointer is updated, which makes it relatively easy for a debugger to know when calls are being made or when you're leaving a call. That's not the case for these older processors. So what that means is that yes, there are functions, or I should say instructions, to make calls, but there are also ways to manipulate the stack directly, which can make call stack tracking a little bit difficult. So I wrote here some notes. Now let me see here. Yeah, so I actually started implementing this already. So I'm not going to be doing that on stream, but I will be showing what I've done because there is currently an issue with it, and I think I'm going to be spending some time this stream hopefully resolving it, but we'll see how that goes. So basically the key here is that I need to detect whenever a jump or branch to a subroutine is made, so JSR, BSR, LBSR, so these are jump subroutine, branch subroutine, or long branch subroutine. We push the current PC to our synthetic call stack along with the return address, which was pushed to the actual call stack. And then whenever the PC is equal to the last return address, we know that we finished the function. So that's pretty much what I've done, and I'll show you that. And we can pop off the top element. Note that we don't look for the return from subroutine instruction, as it's possible to manually return pop ret address from stack and jump to it. So I will show you some examples of that as well. So there's also interrupts. So like software interrupt, IRQ, and FIRQ, which I haven't implemented yet. All of these are actually calls as well. So I also need to detect those. In that they push the PC to the stack, and then once the interrupt handler is over, it pops back. So that's also something that's interesting to show on the call stack. The famous CWAI, which is the what's C stand for again? It's always forget. I know that it's wait for interrupts, and the C is I have to and the. Anyways, I forget. But basically, this is one of the weird. It's the weird instruction because it's an instruction where you call it and then your CPU basically sort of stops advancing and waits until an interrupt occurs. And once an interrupt occurs, then it's able to jump. So this is one of the weird ones. It's caused a little bit of pain for me. It's the one thing where no time passes and stuff like that. So I've always had to do like special exceptional cases around it. Call stacks are no exception for this. I actually had to remove it from my call stack tracking, and it's something I need to revisit. Okay, so let me see here. One second. All right. So what do I have here? Debugger. So yes, so things I've done so far, I've implemented step over and step out. So these are also things that I needed to do, and these are done in terms of the call stack. So once you have like call stack tracking, you can implement features like, I'm stepping over my instructions and here's a call, and I don't actually want to step into the call. I just want to step over it, which is the next instruction in GDB. Which what it does is it's going to effectively, run all the code of that call plus any calls it may make until we finally return to the instruction right following the call. So that's step over, which I guess technically speaking, I maybe could have done. No, I would have, yes, I needed the call stack because I need to make sure that I get back to the same place. Although now I think about it, I think the way I've implemented it would not work with recursion. So maybe that's a problem that I have right now. No, that's true. Because right now what I'm doing is when we're about to do a next, I just look at where I'm supposed to return to and I just set a breakpoint on it. But of course, if ever there's a recursive call, or even not recursion, but like if there's a deeper call that makes a call to the same function, which is in effect a recursive call, I suppose, then this won't actually work. So I need to track more than just, I need to do more than just put a breakpoint on the instruction following the one I'm calling, but also I have to make sure that there's a stack size that matches, what I expect. So, yeah, anyway, that's something I don't have to worry about too much because I don't think we have any recursion right now. There's also step out, which is the ability to say I'm inside a call right now and I just want to finish this call. Also that uses the call stack, so that works. So yeah, so here's some notes I wrote about CWAI. So I wrote here, it is a weird instruction and messes up call stack tracking. When it executes, it pushes return address in all registers, but then the new PC, the program counter, isn't set until an interrupt occurs. Currently, we assume a call instruction does both, push PC and modifies the PC. But with CWAI, this means our call stack frame is incorrect, as it contains the wrong frame address. So you know what, actually, now that I think about it, I just realized that I might be able to simplify my code. Because what I'm doing right now is I'm really literally doing it in two stages. When you call CWAI, I immediately push PC and other registers to the stack, and then I wait for an interrupt. But maybe what I can do is, maybe I can say, CWAI has been, we're presently executing it, and when an interrupt occurs, I know that I'm in that state, and at that moment do the push of all the registers, and then immediately start running the interrupt. And I think if I do that, then I won't be running into the issues I'm running into right now. Yeah, because I say here, after CWAI executes, we would need to wait until waiting for interrupts suddenly becomes not true, at which point PC should have a new value. And we can create, so I'm going to put here just a little note for myself, or modify CWAI so that it doesn't do anything, push registers, until the interrupt occurs. This way, we don't have this delay between pushing registers and executing and modifying PC, I should say. All right, so that's something I'm going to have to get done at some point. All right, but anyway, so yeah, so just taking a step back, basically what I want to do is I'm sort of beefing up my debugger because I need certain functionality for the debug adapter protocol. The other thing that I need to do, and I thought I wrote it down here, but maybe I didn't. Let me see. Did I write longer? No. Oh, I think I know where I wrote it. Hold on a sec. Dev. Vectrex dev. I think it's in here. Yes, okay, here it is. So, as I had mentioned last stream, the reason why I need to do this, the debug adapter protocol, is because I can't use GCC's GDB stub stuff because I can't produce an ELF with dwarf information. However, I do need to have debug information, and as it happens, if you make a debug build, so you pass -g to GCC 6809, which is the fork of GCC that's used to compile C++ or C code for the Vectrex, in this case, it outputs what we call stabs information into the output. So what is stabs, you ask? Let me show you what stabs is. So stabs, sometimes written stabs, is a debugging data format for storing information about computer programs for use by symbolic and source level debuggers, which is exactly what I'm trying to do, right? The information is stored in symbol table strings, hence the name stabs. Okay, so doesn't matter who invented it, but basically, like there's, yeah. So this is the documentation for stabs. It looks something like this. Stab string type, you have stab n, stab d, stab x. So it's a text format, and I can actually show you a real example here. So if we go to Vectrex Pong here, and I think it was in the .s I said. Let me see here. Which one should I be using? RST. So so it ends up in a lot of the files, but the file that is the most interesting to us are these RST files. So for every CPP file, when we compile it, when GCC compiles it, it'll produce this RST file. So I have a few source files here. These are the CPPs, 1, 2, 3, 4, 5. So I should have 5 RSTs. And indeed I do, 1, 2, 3, 4, 5. In fact, I have 6 because there's a CRT0. That's an ASM file where I have to implement certain things for the CRT, but I won't get into that. But let's just say like we take our main here, main RST, because there's a main CPP in here. So main.rst. So just to give you an idea of what that looks like. All right. So here we go. This is basically the assembly code, kind of like an assembly listing with a bunch of useful information. We have here like the actual addresses, the instruction bytecodes in hex. I think number of cycles for the instruction. There's an artificial line number. Then you have the actual instruction in disassembled view here. There's even some interesting, like, they even insert comments here that are kind of cool. But this is not that interesting to me. What I really need from here are all the stabs things. So now right now there is no stabs. And the reason is because I haven't compiled it in debug, right? So if I want to do that, I just come in here. Now in my make file, I have a way to debug, to compile for debug, and I have a task for it. I think I have it here. Run task. Oh, I guess I didn't add it or commit it anyway. That's odd. Unless, let me go see here. Oh, there it is. Make debug equals 1. So what's this diff here? Oh, okay. So I added it here, but I forgot to push the the task file for it. So we can do that right now. We'll just go to our tasks JSON here, and we have make. And I'm just gonna, just for now, I'm going to, so I have a make clean, and I'll add here make debug. And the only difference is when we do make, we'll say dash, what is it again? No, sorry, debug equals 1. I think that's what it is. Yeah. So if I do this, I do think I need to do a clean. I don't yet have very good dependency tracking with my make file here, but it's fine. And we do make debug. So this should run. If it worked correctly, we should see dash G. Oh yeah, so there's dash O0, so no optimizations, and dash G here. So with that, we should now, yeah, there we go. So we should now see some stabs information. So yeah, so this is a stab source. This says here's a source file. I don't know what these things mean. Maybe it's a section that we're about to describe. And then you have a whole bunch of stab stuff here that describes like basically types. Yeah. Like we should see, oops. How do I go back here? There we go. So there's like these stab D here. I think this like gives you the line number in the source file to which this refers to. You know, like here it's saying memcopy, I think, is in base.h at like line 132. So if we will check base.h, base, no? Oh, wrong file. Here, base.h, line 132, or maybe not. Or maybe it's this, line 68. I don't know. I still have to learn about this format. So where's my mem copy anyway? So mem copy is here. Starts at probably line 53. Yeah, I don't know. I need to read more about that. Oh, there you go, 45. Okay, so it's this last number here, 45. So that's the line number for memcopy. And then you can see here that it starts, the executable code starts at line 53, which makes sense. It's over here. These two lines of code correspond to this here, to the D equals dest, and you can see D and dest here in the comments. And then line 54 is the source, loading source into X and storing it into S. That corresponds to this, and then we're going to have a loop. So here you can sort of get a feel for how stabs works, you see. So what I need to do, if we go back to my plan here, if I can, oh, I think I actually lost it. There we go. I'll keep this open. So Vectrexy will parse, so I need to parse all these RST files to gather all necessary debug info. Source file, source to instruction mapping, variable name to address mappings, etc. So basically what we consider debug info. Then I need to implement a DApp server debugger using CPP DApp, which is it's a project that's made by one of my colleagues at work to make it easier to implement the debug adapter protocol in C++. making use of the stab's derived debug info to return info and to set breakpoints, step, etc. So first goal, just source line stepping, no breakpoints, etc. So my initial goal would just be, can we just step in? You know, F10, step in, step over, all that. Breakpoints and being able to look at the value of variables and all that will come later. If I can just get stepping to work, that would be, I think, a nice a nice initial goal. So I said here, in order to do this, I need to first track the call stack. So that's what I've been working on, as I talked about before. Step in, step over, and out. So that's the other thing, which I've pretty much implemented. And obviously there's a little bit more. So yeah, like there's basically parse stabs info, and finally implement DAP. Okay? All right. So where am I at right now? So let me show you. If we go into the debugger and we look, in fact, we open up call stack. Oh yeah, call stack. Here we go. So this is my call stack implementation. We have a stack frame, which is made up of a bunch of information for a call stack. So the callee address, the frame address, the return address. Right now I'm also tracking the stack pointer, which I'll probably will keep. And then you have the call stack. The call stack itself is really just a vector of stack frames. Makes sense? And you basically can push stack frames, you can pop them, then I have a bunch of helper functions. Now the real work comes in using the call stack, so that happens in here, and now I have a bunch of debug code in there to help me find a bug, which I'm going to show you. But the main deal is that you have every time an instruction is executed, so this is the execute instruction. After the instruction has executed, I call this post-op update call stack, and I feed it the state of the registers before, and it can query the state of the registers now, so that it can make, you know, interesting inferences about, do we need to push or pop a call stack frame. So for instance, if I have no call stack, I always push an initial one. This is just so that I have the you know, on the Vectrex, when you start, we always start by executing the what do you call it there? One of the vectors. So I just like having an initial frame there, because we are starting to execute code and we don't have the initial frame. So this, you could sort of think of this a little bit like main. So yeah, think of it as pushing the initial main. So we do that here. But the interesting bit comes, okay, you can ignore this, this is all debug stuff. The interesting bit comes here where I do this, push calls and pop returns. And so here I say, get call op return address. So this is a function that will return a return address if the operation here is itself a call. So in here we say, if opcode at preop PC is a call instruction, return the call's return address. So here you can see that we get, let's say, the operation that just executed. We read the opcode at that program counter, and we check the opcode. If it's any of these, so if it's a LBSR, BSR, any of the JSRs, then we know that it is indeed a call, and we know that the program counter has been written to the call stack. So we just grab the call stack pointer, sorry, not the call stack, sorry, to the stack. So we grab the stack and we just read it. And the 16 bytes, 16 bits there, or 2 bytes, are the address of the return address. For the software interrupt, it's a little bit different because we push all registers starting with the PC. So by the time it's all pushed, we actually need to offset, like we need to take the stack pointer and plus 10 bytes to reach the PC. So there's actually 12 bytes that have been pushed, but the first 2 are for the program counters. So that's what this is about. Similarly, if it's a page 1 or page 2 operation, then we need to read the next byte to get the actual opcode. And for there, we're looking for SWI2 and SWI3. These are more software interrupts. And it's the same logic, because for software interrupts, it's all registers. So we do the same thing as for regular SWI. And that's that. I originally had some CWAI code in here, but I put that on hold for now. So say we know it's a call. This will return a actual return address. And in that case, this is debug stuff. In that case, we push a stack frame and we populate it with all the information we need for the stack frame. Most of the information here is needed just for display purposes, but some of it is needed for us to be able to go back. Don't know why it says that. Okay, we'll look at that after. All right. Hey, how's it going, Bama? Yeah, long time no see. Yes, I remember you. How you been doing? So, okay, so if the stack here, so this is how we do pops, right? So for pops, we're looking to see if the current stack value is, what did I do here? No, sorry, that's just debugging stuff. Oh yeah, so basically we check if the last return address on the top of the stack is equal to the current op, like the current op program counter. So if our current program counter is the return address that's currently on the top of the stack, that means that we just, return from a function, from the top function. So in that case, we need to pop. You been busy? That's good, man. So that's basically the logic for call stacks. Now all this extra code in here is because I'm actually trying to see if I can figure out a bug that I have right now. So let me just make sure this actually builds. Okay, so it's building. I don't know what this is about. Strange. Looks like IntelliSense is a little bit confused here. Let me regenerate the cache. I'm using VS 2019, and I'm using actually its CMake integration. So I'm no longer doing the CMake, -G to generate the Visual Studio project. Instead, I'm just opening the folder that has the CMake lists in it. It's pretty cool. It's not perfect. There are a couple of issues with it, but overall, it seems to be working pretty well. And I kind of like that I don't have to regen the CMake myself, or if I have to, I just kind of come here and I say generate cache for Vectrexy. There you go. Now it looks like the IntelliSense has been updated correctly, so that's good. So let me show you a little bit what it is that I'm dealing with right now. So it's building again. Okay, it's linking. Okay, so there's my, is this the right thing? Oh, it did not load Bedlam correctly. And why is it so slow? That is weird. For some reason, it's running extremely slowly. Oh, you know what? I know why. It's all my debugging stuff. Yeah, it's because I'm logging a bunch of stuff, so it's totally normal. But this is not the ROM I wanted to load. Oh, okay, I see why. I want to load Bedlam. So Bedlam is basically it's always the same thing. It's always the game that gives me the the most problems. Oh, hey Raptor. Yep, episode 100. Yeah, I kind of suck because I didn't do anything special for it, but yeah, thanks. Maybe I'll do something special at 128 or something. Yeah, thanks. Yeah, it was kind of funny because when I stopped streaming for a super long time, I knew I was at episode 98, so close to the 100 mark, and I always wondered, would I ever get to the 100? Would I ever get back to it? So finally, after like what 10 months or so, here we are. All right, so I want to come here. What do I need to do here again? Yeah, I think I need to put some quotes around this. There we go. This is also part of the CMake integration. It's a little bit different. You get these JSON files or JSON files where you get to configure how to launch. That's pretty neat. All right, so there we go. So this is Bedlam. Just gonna pause that. Everything's super slow. Need to get back here. Oh, okay, yeah. Don't break when this exception occurs. All right, so basically this is my debugger. One of the changes actually that I made is that I now show what the current, I show like the disassembled view of where the current program counter is pointing. And the instruction, it will execute when I step. So that's new. And I kind of need this because now that I want to be able to step over instructions, I need to know where I'm at. And there's a dreaded CWAI. But what I wanted to show you is if you type backtrace, you can see the current call stack. So right now there's only this start here. But if we continue, and I break here, and what? I may have broken this code with all my hacks. Let me just try something. So what it is that I'm debugging is that basically there's a point where after after you lose a life and you start the next round, basically I end up with this like sort of stale frame on my call stack. It's like there's missing a pop somewhere, and I'm pretty sure now I know why, because I've been debugging this for a couple days on and off. And I think what's happening is that there are instructions that can modify the stack behind your back, right? And I think that's what's happening. I think this game is being evil. It's like doing a whole bunch of jumps, and then at one point it says, oh, it's a brand new, we just died, we're going to start again. Rather than, cleanly exit out of its functions, I think it just like slams the stack back to a certain position and just jumps into a function that previously it had called into. So really evil stuff and difficult for call stack tracking. If we look at the CPU, I gotta stop using, that's one of the downsides to using the CMake stuff, is I can't use my fast find plugin because fast find is not aware of the CMake, and it bases itself on a proper VCX proj, Visual Studio solution and all that. But I still have the habit of like opening this, and it sort of has like stale information in here, but this doesn't get updated anymore. Like I think if I rescan, it might actually. I don't even know what it's scanning right now. Anyway. So yeah, and speaking about the stack, so let's see here. How can I, if I do like s equals, so this is the stack value right here, right? So, these are things that will modify the stack, of course. Anything that pushes or pops, but those I am detecting. I think there's like one instruction that's causing me pain, and it's the one where you can just set the stack value. So all of these I'm capturing, like these, branch to subroutine and long branch subroutine, return from subroutine, of course, I'm capturing. Those all do what we expect. Now here, exchange or transfer. That's probably something. What is this guy doing again? Because I see here in the case of only first 6 are valid 16-bit register. I don't even remember what this is anymore. But I see here a place where the stack gets accessed, and we're swapping register of destination with register of source. So that's a possible thing that might screw me up. Pushing the CC state, so that's a result of the IRQ handler stuff. So software interrupt, the CWAI instruction. This is part of CWAI. So this I am supposedly capturing. So that should be okay. Go back to looking for stack here. So yeah, so for example, I think just this, load effective address where we specify the stack. So that's an example of something that could screw me up. So push is okay. And also loading here. Well, I guess load from the stack is okay. I guess it would be a store. Yeah, so storing to stack would modify the stack. But that's okay too, because really it's not about that. It's about setting the stack value itself. So this is all okay, I think. Let me see. There was an instruction. All right, let me actually find it again. Oh, this is all debug stuff. I don't know why my F5. Oh. Yeah. Also, by the way, I have a new keyboard here. I haven't updated my information about it, but this is no longer the keyboard I used to have. It's a Kinesis Freestyle Pro. It replaces my, it's still a split mechanical standard layout keyboard, but it replaced my Matias Ergo Pro. The Matias Ergo Pro stopped working, so instead of buying another one, I looked to see if there was an alternative, and I bought this. I actually don't love it. It's all right. The one thing I like about it is the fact that it uses Cherry MX Brown switches. So they are Cherry switches, and those I love. But the form factor and even the build of it is, I actually prefer the Matias. But it was, you gotta try these things, right? Okay, so here we go. Here's a backtrace that I expected. So here you can see that, you know, at the bottom of the stack here, I don't know if it's, hopefully it's clear. I might have to increase my font a little bit here. Let me just see if I make it slightly larger. It's probably a bit better. So here you see that, like, you know, at the bottom of the stack here, or the first thing we called was this F000, which we call start. That's basically where all Vectrex programs start. And then after that, it executed, or it pushed at this address. So we are at this address in the function that starts at this address. So probably we jumped here and then this did another jump. We then are at this address in the function that starts at this one. And then finally here, we're at 0745 in the function that starts at 073C. And presently we are at F41A in F40E, which is a BIOS routine. If you recall, all routines in the F range are BIOS routines, and I have symbols for those because I have, I have symbols for them. So for example, that's why I have start here, and I know that we are now in draw VLP. This is like a draw vector function. And you can see that we are at F41A, which is exactly the address I'm at now, and we're about to, you know, execute an increment instruction here. So if I do like step, you know, we will have basically, we're just executing a bunch of stuff here. And of course, if I check my backtrace now, we are at F412, which is where we are now in the same function. So things I've done, like, so if you do fin or finish, this will run this function till completion, and we should be at the next address in the parent function. So we should be basically in 073C, probably at 47 or however many bytes this is. Usually calls are like 2 bytes. So probably we'll be at 0747. So let's see. Or 48. There you go. It was a 3 byte instruction. So we are now, if I show the backtrace, see we're at 0748 in 073C. So that's what finish does, right? That's cool. If I do it again, I should be in the parent function once more. So we are now at 0736. So this time it was a 2 byte call. And again, if I show the backtrace, so you can see as we finish, we are basically popping stack frames off the stack, which is pretty cool, right? If we step a little bit more, I'll show you what a, you know, if we see like another, oh, okay, so there was a branch subroutine here. So we just branched into a subroutine, and let's see here. So we are now at 073C. So our backtrace should show a brand new function on the stack, and it does. Right here. And if I finish again, we should be out of it. There we go. And I'll just show you what next looks like. So if we can just carefully, okay. So here's a function that if I step, I'll step into it. It's gonna call another BIOS routine, intensity 5F. So rather than step into it, so make sure you can see this, yeah. I'm gonna call next. So if I call next, it's going to actually execute the entire body plus any calls it makes, and brings us to the instruction following the JSR here. And in fact, you can see that we did more, because if I do a trace like this, the trace shows that, you know, we were actually executing a bunch of code beforehand. That, like, this is stuff that was happening inside that function, and then we made it to here. So that's basically it. So, right. So this is what you expect out of, you know, call stack tracking and call stack stuff. So we have next, we have fin, and we have the ability to print our call stack. So these are really, really cool features, and also necessary for implementing our source level debugger. So now, what's the problem? I'll show you what the problem is. I'm just going to pause here. I'm going to put a breakpoint in one of my debugger things that I've been doing. So what's going on is there is a point. Okay, so every time an instruction gets called, we call this post-op update call stack. So this is where I determine whether we need to push or pop. Now, one of the things that shouldn't happen is this here. I actually had an assertion and I was tripping this assert. So I was like, why? Why is this happening? So what is this assert? This assert is saying that technically speaking, the top of the call stack contains a callee address, right? Like the address of the instruction that called into our current stack frame. The current address of the PC should never be equal to that, right? Because if it is, so like just to be clear, the callee is like if I go back here, it's kind of hard to talk about, but whenever you call, you step into a function. So here at 0075, we jumped into this function. So this is the callee address for the stack frame here, the top stack frame. While we're executing in here, we should never reach this address. Instead, what we should be reaching is a return, right? Something that brings us back. And even when it brings us back, it shouldn't bring us back to this address. It should bring us back to the instruction following that one. So I have this check here, to make sure it's sort of like a sanity check, like my call stack tracking is doing the right thing. But actually we are entering this. So this is my little trick to just kind of like get a breakpoint in there. So like, let's say I leave this breakpoint here, and you'll see what happens. So if I'll continue here. Now it's really, really slow because I'm logging a whole bunch of stuff, like I said before. Now we just wait, boom, there we go. So you see we just triggered this breakpoint after we died. So Bedlam is doing something bad. And so if I turn this to true here, we should be able to actually break into the debugger again. So here we are. And if I show you the backtrace, you'll see the problem. This is the problem. We are now, once again, in 0796. We were in 0796. There was a stack frame for it. And then we died, and then it pushed another 0796. You see? If I continue and then die again, and actually, I wonder if it's going to just keep saying this now. Probably. But I'll just, yeah, I guess it'll keep saying that because it is at the top of the stack. We'll die again. We'll break again into the debugger. Oops. And if we backtrace, for some reason I am not seeing it twice. That's odd. Weird, because last time I did this, I had one every single time I died. Okay, and now we actually end, and so this, all right, so now like if I go back to here and start playing again, and then break. So once again, now see here's our third 0796. So you see our call stack is basically invalid, corrupt, whatever you want to call it. So there is definitely something going on here. And that's what I need to figure out, because I need to make sure that my call stack tracking works perfectly. Otherwise, our source level debugging won't work properly, right? let me do this again. So now that you know what the problem is, I'll explain a little bit about the debug info that I've... Hey, oh, I didn't enable my breakpoint. Hold on. Let me re-enable this breakpoint. I can't wait to solve this and just move forward. A part of me is also thinking maybe I don't really need to solve it because, like, one thought I had is if this is one of those Bedlam is doing something weird, I might not have to worry about that in the case of source level debugging, because when you compile your C++ with using GCC, it should not emit any weird code like this. Like, this is obviously hand-coded assembly stuff written with, stuff compiled in C or C++ with GCC should do the proper pushing and like the branching to subroutines and the returning from subroutines as expected. And so probably we won't run into this, but I'm still sort of curious about this problem. If I don't really get anywhere with it, then I'll kind of put it on the back burner and move forward. But I will spend just a little bit of time today looking at this. Okay, so there's our breakpoint. Set this to true because I want to get back into the debugger here. And what I want to do is I always forget how I do this again. I want to trace the last, say, let's start with 10,000 lines into a file. All right. And I'll show you guys some of the debugging stuff that I've collected about this. So if we go into here, debug out, I open this. Okay, here we go. So I did some debugging. This is what actually slows down the emulator, because it's like logging and flushing every single line. And what it does is it's basically the call stack tracking. For every time we push and every time we pop, I'm showing here the instruction that pushed and instructions that popped. And I also have this kind of visual representation that shows you the size of the call stack, which I find kind of neat. So you can see, like, for instance, at this point here, we did a branch to subroutine, and then we did a return from subroutine, right? And you can also see this is the decimal value of the stack pointer. I think it starts off at, what is it again? So yeah, every time we push, it goes down. I think, is this the initial stack pointer? I forget, doesn't really matter. But the point is that every time we push something, the stack pointer goes down by 2 bytes. And obviously, there's other things that push to the stack, so it's not always 2 bytes that we're going to see. Here it actually is. But yeah, and you can see the problem. Okay, I'll show you the problem. The problem is actually visible here. So this is the instruction that's causing us the problem here. At ADB6, at 0229, at this address, we have a jump subroutine. This jump subroutine, if we search for this address, you see that it occurs in many, many places. The thing is, though, when it normally occurs, we are at, basically, we were at one call stack frame deep, and we just pushed a second one. That's what this represents here, okay? But this very last one, you see that we were at the second one, and now we're pushing it at the third call stack frame. So that's the bug. You know, this is not supposed to happen. We should not be pushing this call frame, the stack frame, for this jump while this, you know, as a third stack frame, if you will. So if I just go like up from here, the last time we pushed or executed this instruction, this was the second stack frame, and now it is the third. And that's abnormal. So the last thing I was doing looking at this is I just did a trace of the last 10,000 lines, and if we go take a look at that trace, it's this one here. I don't know if I have enough, but so there's again our jump subroutine. The thing I was paying attention to was the stack here. And I think what I was doing was I was looking to see how much does the stack change, and is there any like, you know, significant jump in the stack size not too far away from here, because I'm thinking that's my problem. CBDE, CB80. So what's this here? See, so this looks suspicious, right? So like not too far away from our problematic jump, we had a stack here of CB80, and then all of a sudden we have CBDE. So that's a pretty significant jump between these two, and in fact you can see here that the instruction is a load stack. So this is what I was suspecting might be the problem. We are basically changing the stack pointer here to another value. And in fact, we're actually in an interrupt here. And after this, we return from interrupt. So what's the deal here? How does this work? This code is so wonky. And you know, I think if I go back and like rewatch rewatch my old streams where I was messing around with Bedlam and trying to fix the interrupt stuff, I probably like would because I don't remember anymore, but in there I had discovered the way Bedlam works, and I know that it's weird. It uses an interrupt to basically drive the game, and I find this a bit strange. Like, let's just see if this is called somewhere else. Oh, interesting. So it's actually called in multiple places. So that's interesting. So this stack jump actually happens more than once. And let me think a little bit about this stack jump here. So CB, so we were at CB80, and now we're at DE, and it's actually explicitly saying load C8, C5 into the stack. Is that what it's saying? Oh no, it's saying load the value written at C8, C5, which is CBDE. So why is it doing that? What's in C8, C5? Oh, so here's a place where we store. Oh, that's interesting. Oh, that's interesting. I see. So we actually, okay. Here's a place where we basically jump into, where's this Bedlam IRQ start come from? Did I add this to my symbols somewhere? I must have. Let me just double check that. Did I put it like in my symbol table here? Because this is where I get all my symbols. Oh yeah, there we go. This is from back when I was debugging Bedlam. I guess I added these to my symbol table file and just left them there. Well, that's remarkably useful. I'm glad it's there. Even though this is like in the symbol table for the BIOS. So it looks like when we start running this IRQ, the first thing that it does is it stores the value of the stack at this address, so CBDE. And then later on, it says, let me restore the value in my stack because, oh, I see. It remembers the value that was in the stack, then it actually immediately writes CB80 into the stack. Why does it do this? Let me think here, CBDE. Just thinking about, does this mean that it's not saving the values of the stack, it's just saving the current stack address, CBDE, and then it's backing up the stack to 80. Okay, so DE is 222, and then 80 is 128. So this is basically saying that our stack, now if I gotta remember, the stack actually, when we push to it, it becomes smaller, the value, right? Yeah. So this is a bit odd. Let me see here. So it initially is CBEA. Right. Okay. So it initially starts off as at 234, and then it goes down as we push. So we are now at 222, and then what it's doing is it's saying, let's bring it down to 128. Okay, so basically it's saying, let me move to an area of the stack that I know is currently not being used. This is really like funky stuff, right? It's basically was carefully coded so that the it was carefully programmed so that, you know, from 234 all the way down to 128, that's like normal program stack, and then starting from 128 down to whatever, I guess down to 0, that's like IRQ stack. I suppose that's what that means. So I guess they'd have to be really, really, really careful here. So they're just saying, let's just save wherever the stack was right now. It's pointing at some address. Let's just save it. And let's force a stack now to point somewhere lower on the stack so we can use this for our IRQ handler. Then later on, it's going to, just before ending the interrupt here, it says, well, let's restore back where our stack was pointing to. So it goes back to CBDE. Okay. So now I'm thinking, is this something that I need to worry about? Is this related to my problem? Maybe not. normally when this instruction runs, whoops, what is our stack pointer? Oh, I don't have it. Oh, maybe I have it in my other file. Yes, I do. So this is 55, so 55220. I should have put this in hex. Anyway, so the stack pointer is always the same, and it's still the same. See, this is so messed up. Trying to think, what am I going to look for here? All right, the other thing I'm thinking about is what I think a little bit about this logically. We have a function that we call, and it looks like, in effect, we're like recursively calling it, which is not normal. So it looks like we never returned from it. What would cause that to occur? Let me try dumping a bit more than 10,000. Maybe I'll have another, if I do 100,000, I might actually have another instance of that jump instruction. I think 100,000 is actually my max. Did this actually reload? Oh, maybe not. Yeah, that's 100,000 lines. So let's see if we hit this guy. No, unfortunately not. All right, so I have the stack pointer here for all these other instructions, so maybe I could find another place where they diverge, and maybe that will help me. So we are at stack 3. That's the same. What about here? To 198. So what I just did now is I'm looking at when we start at the top. You can see that when we are 3 deep, the stack pointer is at 52198. If I search for that in my file, I can see that it only lasts up until here, and then after that, there's no more search hits. So that means that the next time we go to 3, our stack pointer will no longer be 52198. So that's curious. So maybe we can see what that means. Let me just split the screen here. No, okay. Damn. I am not sure I understand what just happened here. If I search for this. Oh, okay. It's just VS Code not doing all the matches. Oh, that's great. That's a bit of a fail. Sort of relying on the fact that it would search through all of it and give me the highlights. Maybe I should try Visual Studio just to see if it's able to crunch this file. Being used by another process. Is this file actually being locked? Oh no, okay, I see. Interesting. So Visual Studio wants to open it in write mode. That's weird. Why? Alright, so let's quit this so I at least can open it in Visual Studio. Alright, here we go. So like we were saying, oh, this does the same thing, I think. That's a shame. Oh no, wait. Okay, this is the end. All right, so at this line here, we don't go further. Let me remove line wrap, like that. Okay, so this is the last line where we see this. Now let me find the next. And again, I want to split this if I can. Okay, we'll split it this way. Whoops. Okay, so what's going on here? Is this normal? So here's the next call. Stack pointer was 198. We return, we're at 200, yes. We return again, we're at 202. Then we jump. I guess it's okay. I suppose it really depends on the size of the instruction. So like for example, this jump subroutine here is a 2 byte. Actually, it's a 3 byte. Oh, sorry, that doesn't matter. No, okay. It's all about the PC and what gets pushed. So it doesn't matter the size of the instructions. So does this make sense? 200, 202, back to 200. Wait, what's this? This is weird. So something between, so obviously we don't see all the instructions here, right? This is just the pushes and pops. But between this guy, oh, so maybe this is the interrupt handler. What we were saying about bringing the address down. I really should be outputting these in hex, because that would actually tell us what's going on here. But this, like, in fact, I guess I could just take this and convert it. CB7E. Does that correspond to what we were saying? Seeing? I think so. Okay, so if I continue down this, (52092). Does this make sense? Now it's 091. Jump subroutine becomes, it went from 92 to 88. Well, okay, at the next branch, that's all right. Okay, back to 90. See, this is weird. We were at 92, and when we come back here, we're at 94. So this doesn't make sense. And here I see that we're doing a pull stack x comma PC. That could be our problem. Maybe. Though we do end up back at 096 here. Oh no, okay. This is very confusing. I think that's because I'm printing the stack pointer after the instruction is executed. So when we push, it's 94. When we pop, we're back to 96. So this actually does make sense. Yeah, okay, that makes perfect sense. And this 91, does this make sense? Suppose it could. We're back on 94. We execute some instruction that moves the stack pointer and we push a value maybe. So now we're in different space. And I guess all of this is still the interrupt handler because we're still low on the stack, or high, depending on how you see it. So when does it go back to being like 521? Oh, it doesn't. So, okay, so it is interesting to note that this pop here, we were still executing the interrupt. And then the next push, we're no longer in the interrupt handler. So it does seem related to that. So, which brings me back to this here. I'm basically missing a pop. My stack pointer is correct. I'm at the right address, but I'm missing a pop somewhere. Something, I guess, between these two here. I guess what I'm missing here is the return from interrupt. If indeed we went from here to here, it means that there was a return from interrupt, but I don't see the RTI here. Do I have any RTIs? I don't. Huh. Huh. So this is RTI right here. Right. I'm not tracking the CWAI that goes with this return from interrupt. So that's that my problem? Is that might just be my problem? Is that I'm ignoring CWAI and this guy takes it, makes calls to it using it. Let me think. If I'm ignoring it, could that mess things up? I mean, I don't really see how. Basically, by ignoring it, it's just saying that at some point I'm executing code and we call CWAI, we wait for an interrupt, and then we start executing code. And the fact that I'm ignoring it for my call stack stuff is just like saying the interrupt code is at the same stack frame as the code that called CWAI. And then it executes code, and eventually it'll do a return from interrupt, at which point it'll just go back to where I was in the function where I called CWAI, and therefore just continue from there. So that shouldn't mess up my call stack. Yeah, really not seeing it. There's the RTI I was talking about. So there's CWAI, at least one of them. There's many of them. Let's find the very last one here. So if we take a look at the stack here, CBDE. Yeah, so this is, we're waiting for the interrupt. Now the interrupt occurs. We're about to jump into it. Then we do our store stack, and then we start running the interrupt. So like basically from my call stack perspective, although we did jump to here, is this the problem? Is it because we jumped to an instruction that then does this? Not really, as long as I return from this guy here. So there's my jump. Let me, no? All right, so there's the jump, CWAI, and then we run until the RTI, which apparently I missed. 92103. Oops. Okay. Jump to here. CWI at 0FD. At 00FF, we did a load A93. And then it's EBF8. It is kind of peculiar, isn't it, that RTI brought us back to 00FF? CBEA. What I'm not understanding is we jump to 00FD. At 00FD, we emit this CWAI that says, when you're done, I want to, so it pushes right away. And then it says, when I get an interrupt, I think it wants to go to, what does EF stand for? Let me see. All right, so what does CWAI look like? There's only one of them. Read operand value. Oh, okay, it's the thing to CC our, it says to AND the CC with the flags register. Okay, so that's what that's about. So we basically AND our flags register with EF, and then we basically wait. We wait for interrupts. Once the interrupts comes in, we read the IRQ vector and set our PC to it. So our IRQ vector would be 00F. No, it wouldn't, would it? I'm really wondering about this here, this 00FF. Whether it should be here. Maybe this is a logging problem. I don't think we actually execute this instruction here. I think we come here, we wait, and then we actually end up here. So that's just a bit odd. And then we jump and we start doing the IRQ. And then at one point we return, and we're at 00FF, which is the instruction following the CWAI. So yeah, this is very odd. I think this is just a trace error on my part. And then we run some more code. Just wondering if we're going to see a, because we have a jump here. Yeah, it's just a jump. Yeah, I don't think I'm going to be able to figure this out. Not yet. Is there a way I could... I'm trying to think what I could put in my emulator to like help me detect this problem when it happens. What is it that I'm looking for? I guess I sort of am finding it. But I'm not finding the source of the problem. Yeah, I'm literally missing a stack frame pop. It's very frustrating. Let me search in reverse. No. No, okay, let me search in reverse instead for 52.2. See, it's very interesting to see the different ways that functions return. So here's a jump to a subroutine, and the way it returns actually is by doing a pull stack bxpc. Let me think about that for a second. Okay, because it knows that it pushed b and then x in between, and then there's PC there. So what it does is, rather than, you know, pop and then return, it just says pull the two things that I pushed so far and also the PC, and this will basically do the job in less cycles to, you know, instead of doing an RTS, which is the more common way to return. What I could do is I could sort of look for patterns. If if I look here, this is always at the third stack frame, so that's pretty good. I'm trying to look at where does it start going wrong. Maybe I can find a clue. Init music buff does a branch subroutine 05. And we do that here as well. That's interesting. F538. Let me see what that is. Yeah, so it is inside init music buff. How did we end up in there? Not sure. Strange. F271. Sound byte. Yeah, so like here we can see our weight recal is much deeper than it used to be. Is that normal? Even just right at the beginning, this call right here, okay, so we have multiple places where we call weight recal, that's why. That's great. This code. Could that be the clue though, now that I think about it? This is a different instruction that's calling weight recal though, so it's not really the same place. Yeah, this looks like some kind of initial phase. So you see, like, for example, like any of these functions here, intensity 7f gets called first at f0df, but then later at f7cf. Which is one stack deeper. So maybe that's what's going on here. There's some kind of like bootstrap and then a jump somewhere. So wait recal is at F0AF, then at F7C5. It's weird that this guy didn't give me a symbol name. F687 init music check. Why didn't I get init music check here? Weird. Yeah, so see, I'm always one stack deeper afterwards. All right, let's try. Getting tired. See, like if we run Pong here, we don't really see these kind of shenanigans. See, like right now we're in some function here, and if we step, so you see, this is interesting. So just to be clear, so this is my code, right? The Vectrex Pong. One of the things that I'm doing is I am loading symbols from the map file that I generated from Vectrex Pong in order to get symbols for function names. And here you can see an example of such a thing. This here, and of course it's got the name mangled, this C++ name mangling thing going, so it's not super easy to read, but this is bios.0, or bios is the namespace, and 0beam would be the name of the function. So if we go to Vectrex Pong and we look for 0beam, beam, not bream. So here we go. So this is the function here that we're calling. So let's say we put like a breakpoint on this. So you see right now we are, what just happened? Breakpoint hit at 0538. Oh, sorry, I put it on the wrong place. I wanted to actually put it on this address. Okay, so we are. We're about to execute this BIOS 0beam. If we look at the backtrace, we're in some code somewhere in 0fc5. And if we just do next, you're going to see there's a BIOS print string call that we're making. There's another 0beam, another print string, a BIOS wait frame. So I think this is our main loop actually. We go into main. So there's our wait frame here. So we have a call to joystick is down D-pad. So that's one of the calls here. Joystick is down D-pad up. So it's like D-pad type. It's going to depend on one of the parameters here. There's another joystick down is down call, which is probably the next one here. So and here everything behaves as we would expect. So here's a collides object call. So this is going to be this function here, collides, where we check for collision. See, here we could actually say step into it. And now if we look at our backtrace, we'll see that we are in main, we're inside the collides object call. If we were to step, we actually did another jump here. So where are we right now? So we're in some function, probably the left, right, these functions. For some reason, I don't seem to have labels for these, which is a bit strange. Probably something with the map or the way I parse the map file. So there's the map file. So yeah, basically I'm parsing stuff in here. So if I look for like left, see it's not in there. So yeah, so for whatever reason, I'm not getting all of these symbols, which is not good. Definitely would want to get this. Object, like object left. All right, I think it's only, I think it's not seeing any member functions in the map file here. These are just global functions, that's why. But the stabs information will have what I need. This is, I don't know why the map file doesn't show member functions. You can see it's very, very small. Yeah. Although, isn't joystick is down? That's a member function, right? So maybe I'm wrong. Yeah. Yeah, that is a member function. So what am I saying? How come it's able to see this one, whoops, but not these ones? So yeah, that doesn't make any sense. In fact, we can see here where it's getting its symbols from. It's got the joystick ones, it got base, it got BIOS and main, but it didn't seem to get any from object. Oh, I see why. Because object is not a CPP file. I don't have a CPP file for this. Even so, this is included. So shouldn't it have generated it for main? I don't know. In any case, what you see here is that if we continue to step, eventually, like this is doing some bounding box collision checks, and then after that we return from subroutine. So again, we are in one of those functions, we're going to step, and now we are outside of it. This is pretty much what we should expect to see in this kind of generated code. So nothing surprising. So I think what I have written for call stack tracking should work fine. Let's look at the RST files. Yeah, it's kind of hard to read, but basically there's lots of RTSs in here. So what I think I'm going to do is I'm going to put this issue of call stack not working in Bedlam to the side. I really was hoping to figure it out tonight, but I think I'm going to need a bit more time. And maybe by starting to implement the debugger and using the call stack for games that we have C++ source for, it might maybe this bug will surface itself in a different context, and it might be easier to figure out than trying to read assembly code for Bedlam where I have no source for it. So it's really much more difficult in those cases. So I'm just gonna make a note about it so I don't forget. And I wanted to put debugger here. So I'm going to say here, I don't know if it's really debugger, but I'm going to say bug figure out, or I'm going to say, what's the problem here? I'm going to say Bedlam seems to, when dying in Bedlam, after the next round starts, our call stack is no longer valid. We end up pushing a stack frame that was already pushed before. This compounds whenever we die, or even when starting a new game. It looks like we do not get the RTS, and actually I should write which instruction it is. I closed everything. This is not the instruction. Oh, right. This is coming from from non-Bedlam. I'm just going to run it again to get. It's coming from Pong. Just want to remember as much detail as possible, so when I look at this again next time, I'll recall what happens. Here we go. It's this one right here. 000229. So yeah, it looks like we do not get the RTS or whatever way it returns from the previous JSR and call. I suspect some stack manipulation or the game is jumping to a known location, so we are missing the pop. Because I mean, I guess that's possible, right? Like it's running, it knows it's inside the context of this function. Say it is already in this function, right? The one that we jumped to. And then somewhere along that it says, oh, we, I don't know what, something, jump us back to an instruction that then will call this. But then again, like we sort of see that in the trace here, that that's not what's happening. So yeah, I don't know. I think I'm going to need way more trace. Actually, you know what it is that I need is I need to see a previous call to this and the code that comes before it. Maybe that's going to help me figure this out. Would be helpful to see what a normal execution or a normal trace of executing this instruction looks like. So Brahim says, for me, either you find a bug in this game or it is like that and working fine on the real cartridge. The thing is that it's not a bug in the sense that from the point of view of the game, when this call happens, the stack pointer is in the same place it was the last time it got called. Do you know what I mean? So the game is consistent stack pointer wise. It's my call stack tracking that is inconsistent at this point. So I'm somehow missing the bit that says pop off this thing on my stack. You know what I mean? On my call stack. So I'm trying through introspection to build a call stack because there's no such thing as a call stack for the Vectrex. You know what I mean? So, you know, it's a little bit of reverse engineering, or if you will, it's kind of like I have to be able to detect when a call is made, what we consider a call, and when a return is made. And I thought it was pretty clever by, you know, initially I thought I would look for specific instructions that jump and it's specific instructions that return. But then I realized that wouldn't work for the returning part just because of the multiple ways you can return by doing stack manipulations, like the pull stack like we saw. So I thought, you know what? I'll be clever. Whenever we do a call, I'll extract the return address from the stack, which is what I'm doing. And I'll you know, every time we execute something, I'll just see, are we at that instruction? The one that, you know, at the top of the stack is the last frame that was pushed, the call, you know, the return address that I've extracted from the stack. As soon as we are at that address, it means that we just return from the function. That's what I'm doing. And I think that's the correct way, or at least the safest way for me to do this. Because then, you know, whatever way the program tries to return, as long as it is, you know, restoring PC back to where it was before the call, I should detect it and pop off the stack. So that's what I've got right now. But I have a situation here, at least in Bedlam, where I detected a call and then it does a bunch of stuff. And then at one point it says, oh, I'm making that same call. like as if it was recursive, but it's not the case, right? And I detect this just because I never expect to see the same call pushed twice, if you will. You know what I mean? And that's what's happening. Yeah, this is hard. Absolutely. You know what? I'm just looking at this call stack here and I'm thinking, I think maybe, Thanks, Brahim. Enjoy your lunch. I'm thinking here, look, when we start, we are at 0229 in the stack frame that was started from the initial vector. And I suppose what's happening is that the very first thing it does is it does a jump. Or maybe a jump subroutine or something. Because that's why we probably end up with this. Kind of like the bootstrapping process. But this here will probably never return. We're at 0229. That's weird. 0229 in 0. That doesn't even make sense. What is this? How could we be in an address earlier than the address of our function? I think that's our clue right there. So let's do this. Let's put a breakpoint on 0229 and see what's going on there. We might be able to figure this out, just spend a bit more time on it. This is a little bit like rubber ducking it, right? Rubber duck debugging. Writing it out makes me think a bit more about it. So if we go here, let's close this. Damn it, I think I lost my, it was 0229, I think, right? Just gonna take one more stab at this, and if not, I'm gonna stop here. Oh, so it was not 0229? See, this is weird. Why does my backtrace not show the same thing as last time? We are currently in start. Oh, there we are. Okay. Oh, I see. So we were running the start code. We get to 0229. So now, what is our, first of all, what does our trace look like? So we're in the middle of start. We get to this point, and we are going to do a jump subroutine to whatever is stored in 0D6E. So we step, and we are now at 0769. But if I backtrace, okay, it says 0769 in 0769. That's normal. Okay, so we're back here. Now I stepped. I'm again in 0769. See if that messed up state again. This here, what is this about? I think this is the bug right here. See, normally we were in 0229 in F00 start, and then we would go to 0796 in 0796, which is what we see here. It's this second entry that doesn't make any sense. I can detect this. Normal backtrace, messed up backtrace. How can this be? How can this happen? So what would I do to discover this? So this would mean that our current PC means we pushed a stack frame for 0796, and then our PC got, yeah, see, this is what it means. It means we were running this function, and then something changed our PC to, like, it jumped to this address, which happens to be the same address. That's it. It must be that when we die, Bedlam just says jump to the same start vector that we normally jump to when from the start here. That's it. That's got to be it. So how do I detect that exact thing? I guess I got to detect whenever PC becomes this, but that happens a lot. Right? That's what I was doing before. I put a breakpoint on 0229. Info break. Yeah. 0229. So that wasn't helpful. Or maybe what I gotta look for is when I hit that breakpoint, but not from a jump. Not from a... let me just see it again. Enable 0. What just happened? Breakpoint hit at 0229. What does my trace look like? Right, you see, this is some special code right here. I think we can see it right here. Even if we step, we're gonna see it right there. Okay, let me just wait. T minus n 100. It's kind of hard to read here. Oh, and there's my other trace. Okay, so what I was looking for was 0229. So if we go back up here, 0229. Why don't I see it again here? There is this one. What? Oh, okay. Okay, I'm just getting confused. No. Okay, never mind that. So yeah, so what I was saying was that for this to occur while we're in 0796, do I have still that trace? Let me see. So annoying. I need to open this file. There. Hopefully I have this information in there. Zero 0796. Damn, don't have it. See, normally, when we're in 0796, we just execute a few instructions and then we return correctly. And our backtrace looks wrong. Oh, but this is when it's wrong. Okay, yeah. What does this mean? It still thinks we're in 0796. That's the problem. Okay, that's it. My debugger says that we're still in 02 because they never popped this guy off. So that's the problem. This is very confusing. And very, I can't even, okay. Debugger never popped this frame off. So that's it, okay. So this is showing where we should be in parent stack frame or parent frame. Okay, so basically what's happening here is normally we would have popped this off and we would have been at 0229 in F000 and then called into here. But because this here is a stale frame, we have a stale frame for some reason. It's still there. Yeah, it's not working. And my guess is that, yeah, while we're still running this, something in this frame causes us to not return correctly while we're in $0796. Something causes us not to return correctly. Return, like RTS, you know? And how can we detect this? Maybe while 0796 is top of stack, track SP, like track the stack pointer, to see if it ever what? So stack pointer gets smaller. So if it ever becomes greater than or equal to this frame's SP. In fact, I should basically, because that would be the other way to detect this, right? Would be that every time we execute an instruction, and maybe that's what I should be doing, rather than look for, are we at the return PC? Another way I could do this is say, is, like I call it SP there, but stack pointer, is the stack pointer, the stack address greater than or equal to the stack address that we were at when we made this call? Because that would imply that we've just returned. Instead of looking, instead of looking for return address PC to track call returns, maybe we should just be looking for when S is greater than or equal to callee S. Yeah. But before I change my code to do that, I'm going to do the looking for this case, because that may actually point me to why this is happening in Bedlam, and then that might be enough for me to first understand what's going on, and secondly to convince me that this is maybe the better way to do call stack tracking. So what I'm saying is, see in here, the way I determine whether it's time to pop the top frame of the call stack is by looking at if the current PC, the program counter, is that of the top frame's return address. And the return address is the one that I read from the stack when a call was made. Now, which is right here. Maybe that's not a good approach. Maybe all I should do is say, because the stack always goes in one direction, right? So, just record the stack value when we were about to make a call. And then after that, just keep looking. Did the stack come back to that? Is it greater than or equal to the original stack that I had? And I say greater than or equal to. Maybe it's exactly equal to. In fact, because it would be weird for it to go. No, actually, I do need to go greater than or equal to, because it's possible. Like, I think Bedlam is doing some massive stack wipe and saying, no, you're back here and I'm resetting you. So yeah, so if it ever gets greater than or equal to. Now, of course, then if that's the case, if I have multiple stack frames, I would need to sort of iterate until all my frames are popped off in that case. So that would be the more, for any kind of drastic stack wipe, like some kind of, let's say there's a game that does a massive reset. It says, oh, you reset? Well, I'm going to wipe everything. I'm going to reset the stack. I'm going to reset all my registers, whatever. If I have a call stack in place, I need to pop everything. So yeah, I would need to do that. Yeah, I think this probably sounds like the right way to do it. In fact, we should pop off all frames, while frame.s is less than or equal to s, or something like that. Or while, I should, just to keep things congruent, I'll say this, while s is greater than or equal to curve frame.s, or something like that. This way, if a game decides to reset this stack to whatever, initial value, and we have a bunch of stack frames on our call stack, we detect this and correctly pop off our frames. Okay, I think this makes sense. I'm going to stop here because it's late, but I should be streaming in 2 days, so in 2 nights, so like on Thursday, where we can hopefully resume this. So yeah, thank you for watching, and yeah, hope to see you next time.